Hello chemists, this is Ms. Placino and you are watching Screencast 10.5 on colligative properties. Today we're going to talk about how the properties of a solution differ from the properties of the pure solvent. And in particular, we're going to be looking at three physical properties: vapor pressure, boiling point, and freezing points. So let's go ahead and get started. Colligative properties are properties that depend on the number of non-volatile solute particles present and the nature of the solvents. Just to kind of clarify some things, when we say non-volatile, we mean not turning into a gas. Alternatively, not existing as a gas. For example, carbon dioxide at room temperature is a gas. If we're going to look at the colligative properties of a solution, we're not going to look at the colligative properties of something like carbon dioxide dissolved in water. Carbon dioxide is volatile and it's going to be able to escape the solution. So when we're talking about non-volatile, we're usually talking about solids that are going to be dissolved in our solvent. Something like sodium chloride or sucrose or calcium chloride. Any of those are fine. But we don't want our solute going and evaporating on us. That would be bad. And the nature, so it depends on the number, not necessarily the type, but just the number of non-volatile solute particles present. And we talk about the nature of the solvent. Different solvents are going to be affected more dramatically. So we're going to focus primarily on water, but there are other liquid solvents out there, things like chloroform, benzene, carbon tetrachloride. Those are examples of organic or carbon-based compounds. Their properties are going to be affected differently than water's. But for our purposes, when we're talking about the nature of the solvent, we're most of the time going to be talking about water. So again, we care about how many of these non-gas forming solute particles are present in our solvents. So again, the properties do not depend on the actual identity of the solute. It's about quantity, not about identity. We'll talk more about that as we get rolling. All right, so first let's think about vapor pressure. Here we have the pure solution, the pure solvent, excuse me. We're trying to represent that with just all the same color dots throughout the Erlenmeyer flask. Remember, for vapor pressure, we definitely need to kind of cap this off. I don't think that's the best picture ever. Because if we don't, the molecules are going to be able to escape and then we'll never really equilibrate. Here's what happens when we add our non-volatile solute. So the little pink dots are supposed to represent our non-volatile solute that's been dissolved. Interpret the picture. When you add a non-volatile solute to the solvent, what happens to vapor pressure? Now, hopefully as you look at this diagram, you think, well, vapor pressure decreases. I can tell that simply by counting the number of solvent particles that are in the vapor phase. Here I have 1, 2, 3, 4, 5, 6, 7, 8. And on the other side, I have only 5. So we see a decrease in vapor pressure. The more complicated aspect of this is trying to figure out why this happens. When you add solute, you can think about it as the solvent molecules get more spread out. Oh wow, this is not good English here. I will fix that. Just from a statistical standpoint, if it's just the pure solvent, all of the particles that are in contact with the air above it are going to have to be solvent particles. So that's just going to allow more of them to have the ability to evaporate and condense, so we'll have greater vapor pressure. If we add a solute, just kind of from a statistical perspective, not all of the particles that are in contact with the atmosphere are going to be the solvent. So just the odds are lower that a solvent molecule is going to be able to evaporate. The other aspect of this has to do with intermolecular forces. If you add a non-volatile solute and it dissolves in the solvent, we know that they have the same polarity or similar polarities, and therefore similar intermolecular forces. So now the solvent particles, which were before only attracted to each other, now there's solute particles for them to be attracted to as well. So now you have more attractive forces, so it's going to be even harder for one of those solvent molecules to evaporate and become a gas. So the effect of adding a non-volatile solute into the solvent is you see a lower vapor pressure. If you're struggling a little bit on the why, that's okay. At least get to this point where we can kind of unfortunately memorize this. Adding the solute lowers the vapor pressure of the solution compared to the pure solvent. And here's kind of what we were talking about before, with the particles being more spread out. You just have less of a chance of the solvent molecules being in contact with the atmosphere. So really what happens is when you add the solute to the solvent, you're going to kind of like lower this entire phase diagram curve. And we had shown this to you during the solids and liquids unit of the previous semester. It might look familiar, it might not, but we are going to be able to see what happens to boiling point and freezing point. So at 1 atmosphere of pressure, we know that this is our freezing point because it's going between solid and liquid. Once the vapor pressure lowers, we can see that freezing point lowers as well. On the other side of this curve, we've got at 1 atmosphere, this curve is going to represent boiling because we're going between the liquid and the gas phase. As the vapor pressure is decreased, we're going to see an increase in the boiling point. So before we just kind of move ahead and start to do calculations with this information, I want to talk a little bit more about why this occurs. Let's see, change the two temperatures, the freezing point and boiling point of the solution. So let's start with freezing point. Solutions, as we just saw in the graph, have a lower freezing point than the pure solvent. My question to you is why? And I'll give you a couple hints. Think about what's happening when a substance freezes. In particular, think about what's happening to the order of the molecules when a substance freezes. And then think about how solute molecules could potentially affect this process. So go ahead, take a minute, pause the video, think about this, see if you can figure it out. So let's take a look at hint 1 first. What happens when a substance freezes? And I told you in particular to the arrangement of molecules or particles. Well, hopefully you're thinking when something freezes, we're going from a liquid to a solid form, so we're going to be making things more ordered. As a liquid, the particles are kind of just all over the place. And then as it freezes, we have to bring them together and make them far more ordered. Be consistent. We'll throw a couple more over there. Now, as solute particles or solute molecules are going to affect this process. I'm going to represent my solute by little x's. You might be thinking that, man, it's kind of a bigger mess. By making it a solution, I've effectively increased the entropy. So if I want to take something that was even more entropic now than just the liquid and try to freeze it, it's going to take more energy. I have to lower the energy of the system even more. It turns out that solutions will not freeze as a mixture. The solute actually kind of gets pushed out. For example, if you were to, go to Antarctica, which is basically just a big block of ice, and you were able to pick up the ice and taste it, even though it's sitting in salt water, that is going to be just pure water. You are not going to have the salt trapped in there as well. That's because when a solution freezes, the salt isn't going to be able to come with it. So I should say more specifically when the solvent freezes. So solute molecules are going to affect this process by making kind of a bigger mess to begin with. So it's going to take even more energy. We have to lose even more energy to end up with our frozen solvent, and then our solute gets kind of pushed out of the way. This is why we put salt on ice. When the salt melts it's going to, or I shouldn't say when the salt melts, when the salt comes in contact with the ice, they're eventually going to melt. And that's because now the water can't stay frozen as ice because it's formed a mixture. So you have to get to even colder temperatures to get it to freeze. And the overall effect is the ice melts. People commonly make the misconception that the ice is melted by the salt. That's not true. Ice does not get melted by salt. The salt is just making a mixture, a solution with the ice, and that solution is unable to freeze. So it looks like salt is melting the ice, but that is not actually what's going on. This one can be kind of conceptually difficult to think about. So again, if you're stuck, at least remember, okay, we've got a lower freezing point with a solution than we do the pure solvent. Let's look at boiling point. Based on the graph, we saw the solutions have a higher boiling point than the pure solvent. Again, I want you to think about why, and I'll give you a couple of hints. First off, think about what's happening to a substance when it boils. Again, go on the molecular level. Second, how might solute molecules affect this process? So pause the video, see if you can figure it out. Okay, anytime we have boiling occurring, we're going from the liquid phase to the gas phase. In order to do that, we need to basically just obliterate the intermolecular forces of attraction that exist between neighboring solvent molecules. The second I throw a solute in there, now in addition to just, we'll use water as an example. We know that water has really strong hydrogen bonds, very powerful attractive force between neighboring water molecules. So in order to boil, we have to break this IMF. Once we throw a solute in there, let's say something like sodium chloride. I have my sodium, ions, my chloride ions. I'm probably going to need more space than that. But now, in addition to being attracted to one another, the water molecules are also attracted to the ions. Sorry, it takes me a minute to draw the water molecules. So effectively, adding a solute to the solvent has increased the total number of intermolecular forces. Water molecules, or more generally solvent molecules, were always attracted to each other. But now that a solute is present as well, they're going to be attracted to each other and attracted to the solute. As there are more and more intermolecular forces, it's going to be harder and harder to break them. You're going to have to put more and more energy in, get everything moving around much faster so that the water molecules can kind of, I guess for lack of a better way to explain it, break that attraction between not only other water molecules, but also with the solute. So since we have to put more energy in, we're going to see an increase in boiling point. So the way I like to remember what happens to boiling point and freezing point is a picture pulling on a thermometer, like holding it straight up and down. So there's our thermometer, and then pulling from either end. The boiling point is up towards the top of the thermometer, and it's going to get even higher. The freezing point is down towards the bottom of the thermometer, and it's going to get even lower. So that's just kind of how I remember what's going to happen to my boiling and freezing points. From a New York State perspective, that's great. This is basically the takeaway. Do you know what happens? We've kind of addressed why, taking it a step further, and we're going to go even one more step, and we're going to talk about predicting how much boiling point and freezing point will actually change. This is the formula, and this formula is not provided on your reference table. We've got delta T sub B equals K sub B, lowercase m I. So let's first talk about what these different things mean. We know that delta is always talking about a change. T is temperature. The lowercase, I should say the subscripted lowercase b is talking about boiling. So really the temperature of the boiling point. K is a constant. This will be provided to you based on what the solvent is. Lowercase m is molality. And you can think about I as number of particles. Spend a little bit more time talking about that in just a minute. We've got a strikingly similar formula for freezing point change. The only thing that changes is now instead of sub B for boiling point, we have sub F for freezing point. And I'll erase this so it's a little bit easier to see. These are the freezing point and boiling point constants for water. And if you're worried, do I have to memorize these? No, I'll provide them. I'll just expect you to know how to use the formula. So every time you add a molal concentration of particles in solution, the boiling point of water is going to increase by about 0.5 degrees. And every time you add about a molal of solute particles into solution, your freezing point is going to decrease by nearly 2 degrees Celsius. So if we start kind of thinking about this, if I want to calculate the change in freezing point, I've got my K sub F. I can calculate molarity if I know how the solution was made. It's I that's going to require a little bit of thinking. I is the number of particles produced by the solute when it dissolves. So I want to look at these 3 examples. I have glucose, sodium chloride, and calcium chloride. We've been talking about dissociation a couple different times already in this unit, so hopefully there are really no surprises here. Something like glucose is covalently bonded, so when I drop glucose into a beaker of water, for example, the glucose molecule does not break apart. So I would be equal to 1 here. Sodium chloride as an ionic compound will dissociate or break apart into ions. I'll make sodium plus ions, and I'll make chloride minus ions. And based on the subscripts, I make 1 of each. So 1 mole of sodium chloride is actually going to produce 2 moles of ions. Finally, with calcium chloride, I've got Ca2 plus ions, I have Cl minus ions. Based on the subscripts, I know that I have 2 chloride ions formed every time 1 mole, or I guess I have 2 moles of chloride ions produced every time 1 mole of calcium chloride dissociates. So 1 plus 2 gives me I equal to 3. So if I have a 1 molal solution of glucose, sodium chloride, and calcium chloride, which one is going to have the greatest impact on the freezing point of water? Hopefully you're thinking it's the calcium chloride. K sub F is going to be the same for all of them. If I have a 1 molal solution of each, M doesn't change. The only thing that does change is the value of I. The more particles produced by the solute, the larger the impact is going to be on the boiling and freezing points. Oh, I have it written there again. Osmotic pressure. This is something that comes up on the SAT too. I'm not really going to hold you all that responsible for it, but I wanted to talk about it. In biology class, you probably remember hearing about this semi-permeable membrane. So basically a barrier that is going to allow some things to pass through it, but not all. If we have solution on one side of the semi-permeable membrane and just the pure solvent on the other, so the solvent is represented by kind of this like lime green or slime green with all these little dots. Our solute is the blue particles. What's going to happen is the solvent is going to be able to flow through that membrane. So the pure solvent is going to flow into the solution, effectively diluting the solution. And this process is going to stop when the pressure on the solution side is high enough. So basically you've got gravity pushing down on both of them, and then we're going to stop because essentially the force pushing down on the solution side is going to counterbalance the flow of the solvent through the membrane and the gravity that's pushing down on the solvent side. So you can be aware that this is another colligative property, but this is not one I'm going to hold you responsible for. I'd like to wrap up with a practice problem, really just to show you how to use the delta T formulas that we talked about. So I'm looking in your workbook and I'm taking a look at practice problem number 1. And it tells me that 2 moles of glucose are mixed with 500 grams of water. You know what? I'm going to skip this one. I lied. I want to talk about number 2 instead. Sorry about that. I've got 3 moles of ammonium bromide dissolved in 250 grams of water, and I want to know the freezing point and boiling point of the solution. Okay, so a couple of things that I need to do first. Let's look at the formula. So the change in we'll do freezing point first, is equal to KFMI. So I'm trying to figure out the change in freezing point and ultimately freezing point. I am dealing with water, so this has been provided. It's 1.86 degrees Celsius per molal. I need to know the molality of this solution. So molality is equal to moles of solvent divided by moles of solute divided by kilograms of solvent. So I've got my 3 moles of ammonium bromide divided by 0.25 kilograms of water, and I come up with a very concentrated solution of 12 molal. I'm going to plug that into M. Finally, I need to know the I value. Ammonium bromide is an ionic compound, NH4 plus and Br minus. So when this dissociates, I'll make my ammonium ions, and I'll make bromine ions, and they're going to be in a ratio of 1 to 1. So in this case, my I value is equal to 2. Every time 1 ammonium bromide is dropped into water, it's going to break up into 2 ions, NH4 plus and Br minus. From here, it's really just straightforward multiplication. So the change in the freezing point of the solution compared to the solvent is going to be negative 44.6 degrees Celsius. So the freezing point, usually the freezing point of water is 0 degrees Celsius. I'm going to lower that by 44.6 degrees Celsius. And that's my freezing point. Let's do the same thing with boiling point. I know that the change in the boiling point temperature is equal to the boiling point constant times the molality times the number of particles. I've got my boiling point constant as 0.513 degrees Celsius per molal. I've got 12 molal solution. Oh geez, I'm tight on space, so I can move this over. There we go. And I know that I'm going to produce 2 particles from my solute. So if I take 513 times 12 times 2, I end up with a change in boiling point of 12.3 degrees Celsius. In order to find the new boiling point, I know that water boils at 100 degrees Celsius. I'm told that the change in boiling point is 12.3 degrees. We see boiling point elevation, so I'd have a new boiling point of 112.3 degrees Celsius. All right. That is how you're going to solve those problems. I know that's a lot of hoops to jump through, but these are really good conceptual questions. Yeah, I can get you to, if I give you the name of the compound instead, you're going to have to know the name, or how to take the name and turn it into a formula. If it's ionic, you've got to be able to dissociate it into the correct number of ions. Then you'd have to find the molar mass and convert mass into moles and ultimately into molal. So that's already just so many different things that we've talked about first semester. Then we get to use colligative property information. So in my opinion, it's really not the formulas itself that are difficult. It's kind of all the supporting things that you need to really solve problems like this. Taking things like the name and turning it into a formula, dissociating, coming up with a total number of particles that are going to be produced. So be really careful with these. And again, I strongly suggest working on the practice problems, and if you feel like you need to, go back to the fall semester topics and try to refresh your memory a little bit. I know I've said it before, but it's usually not the new information in the solutions chemistry unit that proves to be kind of the downfall of chemists. All right, that's all I've got for today. Thank you for tuning in. I hope you found this helpful.